So image size, we're just going to change.
All right. So let's start it. Let's do Coro of Tina.
Oh yeah.
Caleb. Anish. Anu. Natural. That's it. Joshua. Cole. Jacob. John. Handle. Okay. More. More. I have it. Song. Size. Syria. Swazi. Taylor. Vijay. All right. So, how's your assignment going? Now let me discuss two things. So first, part 2 and part 3, the data, actually part 2 and part 3 are totally independent of each other. So don't try to use the result of part 2 to predict the housing price for part 3. So I gave you the data set, right? Train.csv and test.csv. This is only for part 2. So based on the training set, you will determine W0 and W1. Then you will retrain your model by using housing train.csv. And then after that, you have 2 ways to do it. Since you have W0 and W1, you can manually calculate it. Or by using W1 and W2, W0 and W1. Or you can just save this one as a testing file, so then it can be predict. So anyway, for this one, you need to change code a little bit, so probably. If you don't want to change code, you can just provide the training set as testing set. So then you can design again with W0 and W1. So usually, also some of you directly send your submission to my, to my email. From now on, all the submissions should be going through D12. So submit your assignment through D12. Never send me an email. Also, So far we have 37 in this class and only 17 submitted. So what's wrong with you guys? I have extended deadline to midnight, so 11:30 tonight. So I just found out that I gave you more than 1 week to finish this assignment. It didn't help. So you guys always waited until the last minute to get it done. Then I will keep. If you prefer a shorter deadline, I will make it shorter. So that I will push you to work on it from early time. But anyway, so the deadline is 11:30 tonight. And if you really need a teammate, then just let me know. So we can dynamically accommodate your request. But anyway, if you're not confident with your programming skill, then this is not the right course at this moment. But still, if your math is not good enough, you can still survive because I can provide all the equations you need to implement the algorithm. Okay, so do you have any questions? All right. Now, let's review what we studied so far. So we have already expanded our simple model to a little more complex model, which is the linear regression with multiple features. So the lowercase m still represents the number of training samples, n represents the number of features. Yeah, still, my tongue is recovering. So if you have difficulty understanding, feel free to stop me. Okay, so how do we distinguish different training examples? We use superscript, right? And we have multiple features. How do we distinguish different features? Subscript. We use subscript. So, we utilize all the symbols to the extreme, right? So the superscript represents different training examples, and subscript represents different features. Okay, then in last class we figured out the traditional way to implement the gradient descent algorithm. Actually, theoretically, the gradient descent algorithm only consists of one line of code. So we just keep updating the weights until it converges, right? But if we implement it in a traditional way, then we go through all the training examples. So that's from 1 to n, right? Then in the first step, we calculate the output of the hypothesis function for a particular training example, right? Then we calculate the square of the difference between the output of the hypothesis function and the target output. The reason is that this is the cost function, right? So sigma is translated into loop 1 to m. So now we want to accumulate this. Then for dwj, that is this part. So that is xj superscript I times the difference between the output of the hypothesis function and the target output. That is this part, right? Yep. Okay. Now j is equal to is greater or equal to 0 or less than or equal to n. So basically, we should have n+1 such kind of update rules. If we have n features plus the fake attributes, which is W0. So then how would you, once you finish this loop, then how would you update the cost function?
1 minus 2, right?
So
by
E divided by
2m.
2m. So the whole thing represents the summation, right? So then once we finish that, we calculate the E divided by 2m. Then how would you update the dwj?
By
dwj is divided by m. Then how would you update wj?
equals WJ minus
alpha.
So that's wj is equal to wj minus alpha times dwj. Okay. Then are we done?
Repeat.
Yeah, so we should repeat until convergence. So repeat this process. This is just one iteration, right? Then we may have, by default, I give you 1,500 iterations, right? So there are two ways to stop. One way is to determine the number of iterations. Or if you think, E is good enough, for example, it's very close to 0, then we stop. So basically, this is the traditional way to implement the gradient descent. And this is how you should do in your programming assignment 1. So if you understand this, then you have no problem implementing programming assignment 1. Okay, do you have any questions for the discussion? Okay. So we have already know that for a specific training example, I forgot to bring my cheat sheet. That's okay. So for a specific training example, we can write the hypothesis function in this way. But normally we don't like the formal notation because it's very abstract, right? So this is what you like. So that's W0 times X0 superscript I, then W1 X1 all the way to Wn Xn. So then what is Xi? X superscript I is X superscript I 0, 1 all the way to n. So this is a column vector. Remember that we have, so how many features do we have, for this particular example? We have n features plus the fake feature, which is always equal to 1. Now what is W? So for each feature, we should have a weight.
Yeah.
So basically, W is W0, W1, all the way to Wn. Now, how do we use the matrix operation to implement this one?
We have the transpose.
Okay, very good. So basically, we use W transpose. We use W transpose equal to W0, W1, all the way to Wn, and times X0, X1, So according to the rule, according to linear algebra, so it's equal to this one times this one, right? So W0 times X0 superscript I plus this one times this next one, W1 times X1 superscript I equal to, all the way to this one times this one, Wn. So they are equivalent, right? So basically, you know, this one is equivalent to W transpose times X.
So we don't need a summation if we multiply the matrices, right?
Hmm?
We don't need to like have a summation or a for loop.
For programming assignment 1, you don't. So that's the topic of programming assignment 2. So I will try to release the programming assignment 2's requirements and the data set over this weekend. So actually you can start, if you have already submitted, now you can start to vectorize your code, right? So you know, without my guidance, now you can start to work on programming assignment 2. So is that clear for this part? W transpose xi. So this is clear, right? Okay. Then I also presented the efficiency of vectorized version. So if you use non-vectorized version, it's going to be very slow. But if you utilize the vectorized version, then it is more efficient. So the general rule is whenever possible, avoid using for loops. So because for loops are very slow, you are not utilizing the optimized feature of Python and NumPy. Then we should use NumPy functions to manipulate a matrix. For example, you want to calculate the exponent for each of the items in vector x. So instead of using for loop, you can directly use np dot exponent x. And in addition to exponent, you also, you know, NumPy provides almost all the commonly used functions such as log, absolute value, square root, etc. In last class, we studied the idea of broadcasting. Actually, we solved here. So sometimes I want to get the submission. For example, I want to operate each column individually, and sometimes I want to operate on the rows. So now, for example, I want to get the submission of math, science, English, and literature, right? So you know, just sum up all these values. So how can we do that? You know, the idea is we can use the operation. If this is the matrix A, then if we call matrix A dot sum, then use axis is equal to 0, then it means that we are operating columns. Then if you put axis equal to 1, it means that you want to operate rows. So now let me show you. Okay, so basically I have copied the data to here. So A is equal to MP array like this. So I can calculate MP sum x is equal to 0. 8. Okay, so you see, if I put axis equal to 0, it gives me 4 values, right? So for example, this one is easier. So 200, 305. So that's 305, right? So for this one, it's not typical. So, you know, 82 plus 98 is going to 180. Then plus 66, then 246. So basically, you know, the operation is column-based. Okay, now if I change it to 1, you see, it gives me 3 values. So why it gives me 3 values?
Rows.
Because it adds up all the items on a row, right? So then it gives me 3 values. So this is the idea of this is the functionality of axis. The value of axis can control whether you are operating columns or you are operating rows. So is that clear? Yes.
Can I do both columns and rows?
Then you will just get a single number, right?
Yeah.
Yeah. So in that case, you can one way you can do is like this. Number until sum. So if now we don't use this one, use matrix A, we use np.sum, then we get the summation of all the values. So is that clear? But I didn't try, but if I don't say anything, what's going to happen? So now let's see. Probably it's the same as np.sum. Yeah. So is that clear? So if you don't say anything, then it has all the elements together. So easily it's fine. You can use np.sum or you can use a.sum. Sometimes, based on the summation, I want to get percentage. For example, I want to see, how does Tom contribute to the math grades. So, for example, this is the code. The reason that we want to reshape, then the idea is not an issue. Axis. You see, if you get the summation based on columns, then the result is 4 comma. So this is called rank 1 array in NumPy. So we don't like array like this because it's not very convenient to operate. So that's why normally we reshape it. For example, if I reshape this B, right? So B dot reshape. I change it to 1 row and 4 column. So you see, now I change it to 1 row and 4 columns. So that is 1 row, 4 column. Each item is corresponding to the summation of a column, right? Then in that case, I can calculate the percentage for A. Percentage 100 times A. So it's interesting. So if I use 100 times A, what's going to happen?
Every element in the matrix.
Every element is multiplied by 100, right? So this is called broadcasting. So over, that is B. So B has been reshaped. Okay, then I can print percent. Let's verify the second column because in most of them are almost 100. So it should be around 33, right? So that's 32, 32, and 34. So is that clear? So you see, now let me do this. Okay, so what is the shape of A? 3 by 4, right? 3 rows and 4 columns. 3 by 4, and the shape of B is 1 by 4. The shape doesn't match. But the idea of broadcasting is that it duplicates B multiple times, then just operate on each of the rows. So now let's generalize the rules. So if I give you a vector 1, 2, 3, 4 plus 50, so what's going to happen?
51.
So basically, NumPy will duplicate 3 times, right? Then it's going to be equal to 51, 52, 53, and 54. Okay, so then what's going to happen for this one? 1, 2, 3, 4, 5, 6, plus 10, 20, 30.
It's going to be 11, 22, 33, and 14.
Okay, so basically, it stack another one here. So now the shape is the same, right? Then it's going to be
11,
22,
11,
22, 33, 14, 25,
25, and 36.
So this is the idea, right? Okay. Then how about this?
It's going to duplicate 3.
So it duplicates 3 times, right? So that's 20, just like this. Then it's equal to 11, 12, 13, right? Then 24, 25, and 26. Yes.
Does it always, does it have to match one of the values? Like it has to be the same length on one of the cells?
Yeah, that's right. So, for example, if you make it 40, then you will get an error because it's difficult for NumPy to broadcast the size of 1 by 4 because it doesn't match. Then the general rule is if you have a n by 5 matrix which operates another 1 by n, then basically you will duplicate the same row m minus 1 times to make it m by n. Then the result is m by n. Now similarly, if you have a column that is m by 1, so you will stack more, the columns n minus 1 times. So you make it m by n, then the result is still this one. If you add a number, then every element will add a number. If you subtract a number, then both elements subtract a number. Yes.
If we have a 4 by 4 matrix and then we were to try to add a 2 by 2 matrix, would that also error out?
For that one, we need to try. So yeah, that's a good question. So let me change this one to 4 by 4, right? So just by adding another row. With 4 by 4. Now let's. By 2, right? Yes. I guess it will give you an error. Yeah. So it doesn't match. So basically, it just aligns through column, vector column, or column vector or row column.
It says it's 3 by 4.
Yeah.
Which means
I guess A.
You had to run that again.
Oh yes, that's right. Yeah, still doesn't match.
So, what if we have what if we have a 3 by 4? Would that be also an error? Because
yeah, so if that's 3 by 4, you should still get error. So now the beauty is that you can do the experiments, right, line by line. If you are not sure, then you can do a little experiment and try your code. Then you will have the confidence. Okay, so now let's go back to our algorithm. So let's see how to vectorize our traditional implementation. If you understand today's lecture, then basically you have done your programming assignment too. So we have already studied how to vectorize this one, right? So how h of xi superscript I is equal to transpose times x superscript I, right?
Yeah.
Okay, so basically, let's start with this one. We know that W transpose equal to W0, W1, almost. Two x I 0 x 1 something like this, right?
Mm-hmm.
Okay. Then if we use W transpose times x superscript I, no, sorry, there's no such case. This one, right? Then we are going to get this the same equation. So this is equal to h of x superscript I. So then we can vectorize this. But the problem is that we have a set. We have a set of values. Now let me copy x I 0, x I 1, x I. But we also have x I x 0. So we start x 0, x 0, 1. Remember that we have m many examples. It's going to be m minus 1. So let's assume we number all the tuning examples from 0, right? X. So we have m tuning examples. We have m tuning examples. Then each tuning example in this matrix is represented by what? Each tuning example is represented by a row or by a column?
By a row, right?
So each tuning example, we have m tuning examples, right? Then each tuning example in this matrix is a row or is a column?
It's a column.
It's a column. So for the ith tuning example, we have x superscript I, then attributes from 0 to n, right? Then for the first tuning example, which is 0 x superscript 0, then we have attributes from 0 to n. So this is equal to big X. So is that clear? So in our training example is provided in terms of So what's the shape of this matrix?
And then
It's
N plus one
plus 1 by m. So what is lowercase n? Number of features. Then m is training examples. So basically, we have m training examples. So this is the first training example, second training example. Each training example is a column. Is that clear?
Yep.
Do you have any questions? And we have already know that W transpose is equal to W0, W1, all the way to Wn, right? Okay, then if I use W transpose times the entire matrix, what's going to happen?
It's just going to do the broadcast, right?
So what is the dimension for W transpose? 1 by
N
n plus 1, right? So this one is n plus 1 by m. Then if I use W transpose times x, according to linear algebra, the resulting matrix, the size of the resulting matrix is 1 by m. So what does that mean? So, for example, I have already told you, if I use W transpose times a specific training example, what does that mean? If I use W transpose times x,
It's
this is what?
x times w plus.
This is hypothesis value, right?
Yep.
Okay, so basically, if you use W transpose times x, then basically you get, for example, I call it y hat. So it's going to be, for this one, and this one we get y hat 0. This is the prediction for the first training example.
Yep.
Then for the second one, then for the ith one, so that's y superscript I hat. Then this. So is that clear? If you use W transpose to multiply the entire training set, you will get a set of outputs. So is that clear?
Yep.
Yes.
So y hat is the predicted value and y is the true value?
Y hat, if you use W to time a specific one, which is W0 times X0 plus W1 plus times X1 all the way to Wn times Xn, it's going to be what? It's given by P. It's going to be the output of the hypothesis, right? That's why I put a Y hat. This is not true output. And where is true output?
The test set.
So true output is given because it's supervised learning, right?
Mm-hmm.
The true output is given. So we have, for the first one, we have Y0. Then for the i's, we have Is that clear? Yeah. So if we use W transpose times x, then you are going to get a row vector of hypothesis output. So each element is corresponding to the output to a specific training example. We have m training examples. Definitely, we will get m outputs. So is that clear for at this point? So do you have any questions? Then y is given. So because this supervised learning, every training example has an output.
So you can just compare those two numbers.
Then can you calculate the difference between the hypothesis and the true label?
Yeah.
How do you do that? That is y hat minus y equal to, that is y hat 0 minus y0 y hat I minus yi. Then it is y m minus 1 half minus 1 times 1. It is still a row vector. So is that clear for that part?
We don't need to transpose it.
Can you get someone to show? Okay. Can you please close the door? Okay. So is it clear now? Okay. Yes.
On the earlier, like the top one, why do we transpose W and not transpose Y?
So if we don't transpose W is a vector. Vector is, the vector size of vector is n plus 1 times 1. It doesn't match the matrix multiplication. So for matrix multiplication, you should make the column equal to the row number of the second matrix, right? So if you directly use a matrix operation, then it won't work. Okay, so since this is the most difficult part, now let me do it one more time. So now let me. Yes, actually, you probably you guys chose the wrong career direction. If you choose mathematics, then that's fine because it doesn't change over 200 years. But as computer science guys, we have to keep learning. Okay, so back to your question. So vector is W0, W1, W2, Wn. So this is n plus 1 by 1. Right? Okay. Then we have x. X equal to, let's have the examples starting from 0. Then 0, 1, 2, n. And then go to ith example. 1, 2. Now, what's the superscript of last one? Minus 1. Why? Because we are starting from 0, right? So if we start 1, then that's superscript. Okay, so this is x. So can we directly use w times x?
No.
It won't work because it doesn't match. This is n plus 1 times 1. This one is n plus 1 times m. So it doesn't match. So n plus 1 times 1 doesn't match n plus 1 times m. So in order to match, you should make it 1 times n plus 1. So n plus 1 matches n plus 1. So it's going to be, output is going to be 1 by m. So basically, the idea is So we transpose it. If we transpose, then it becomes W0, W1, Wn. So now it becomes 1 times n plus 1, right? Then how does that work? So we can work on the first one. So this one times this one, right? For the first column, that is W0 times x0, 0 plus
W1.
this one, W1 times x1, 0, then it's going to be Wn times 0, n. So this a single value, right? This is h of x0. And this is a single value which is corresponding to the output here, right? This our output here. Then if you operate the second column, then you will use W0 times x1, 0, W1 times x1, 1, and so on and so forth. So then you get the value of another output. So basically, then if we use y hat to represent the output of, W transpose times x equal to y hat, then is this going to be h of x0, and this one is h of x squared I, and this one is h of minus 1. Is that clear? So this is y hat. Then y is what? Y is, for example, 0, yi, y and minus 1. Where do you get y? It's given.
Yeah.
Because this supervised learning. So for every training example, all the y's are given. So is that clear? So in that case, we if we calculate the difference between y hat and y, then it's going to be h of super x minus y0, h of super squared I times y of I, then h of x and minus 1 squared minus y minus 1. So this is y hat minus y, or equal to h of x minus y. So is that clear for this one? For this part? Yeah, actually, we are getting closer to our conclusion. So now we have already calculated this part, right? So then how would you get, for example, for this one, you need to get the summation. Okay, so probably let me start with a simple one. So we want to calculate the square of the difference, right, for each of the i's. Okay, so in linear algebra, so if I give you a row column, for example, A1, A2, AN, then how do you calculate A1 square, A2 square, and all the way to n square? How?
Transpose.
You transpose. So for example, this is A equal to this one, right? Then transpose A is equal to A1, A2, AN. So if you time A times A transpose, then it's going to be A1 a1 squared plus a2 squared plus all the way to an squared. So this is exactly what we are looking for, right?
Yeah.
For this one. So, you know, we want to get a summation of all the square. So you see, we have calculated the difference. That is y hat minus y. Then if you want to calculate the cos, then it's going to be 1/2m times y hat minus y times y hat minus y transpose. So it's just so simple. You know, I use the whole screen to explain everything, then you just use a simple line of code to get it done. Oh, okay, so I will have to solve here, so you have the entire weekend to understand how it works, right? Okay, so remember the submission deadline has been postponed to midnight. So make good use of it. If you have questions, send me an email. So don't ask me to debug your program. So I don't have the time. Yes.
So with this